Welcome back to our three-part series for getting started with the SRS Python driver for the SR860 and SR865A Lock-in amplifiers. Previously, I've shown you how to install the driver and then talk to it from the command line. Of course, when using the lock-in regularly, you won't want to type these commands over and over again, and you don't want to be forced to remember what the commands are when you're working in the command line. You will want to write a script to automate these operations, and you might want to work in a development environment that helps give you some context tips. I'll open the folder where we previously created our Python virtual environment and installed the 860 driver with Visual Studio Code. VS Code is a freely available editor with many useful plugins for developing Python code. I'll go ahead and create a new Jupyter Notebook in this folder and call it SR860 demo.ipy notebook. When I do that, VS Code realizes that I'm writing Python code and asks to install the Python extension. Go ahead and do that. To make use of the SR860 driver, we need to tell VS Code to use the Python virtual environment we set up previously. Click Select Kernel and browse Marketplace for kernel extensions. Go ahead and install the Jupyter extension. If we go back to our notebook, you'll see now that the kernel has been replaced by the venv that we created previously in the folder where our notebook exists. Then we start as we did before by importing the needed modules. From SRS inst SR860, import the SR860. And if you're using USB or GPIB, we'll need PyVisa as well. VS Code might tell you that you need to install the ipy kernel. Go ahead and do that. Once that's done, we can connect to the instrument just as we did before, using your preferred interface. I'll use VXI11 and the IP address from the instrument. A great thing about working in an editor like Visual Studio Code is that you get helpful context tips and auto-completion suggestions as you type. So if I start to type check, I see check ID is available right here. Let's say I want to fetch the values. If you remember the get values command, but you don't quite remember how it works, you get context tips here showing that parameters are required. And if you control click on the method or right click, go to definition or press F12, it'll actually take you to the source code that defines get values. And you can see that 2 parameters are required and a third parameter is optional. And under the hood, it simply sends the snap query with the parameters that you've provided. So I'll finish the command with X and Y. And we get a measurement of 50 millivolts on X and tens of microvolts on Y. Now you can write reusable Python code to control your instrument. You can create your own initialization routines, measurement sweeps, and so on. In fact, I've translated the Getting Started guide from the previous video into a Jupyter Notebook so that you can interactively step through on your own time and find all the 860 commands and methods that we learned collected into a single place. You'll find the commands for establishing a connection via the various remote interfaces, serial, VXI11, GPIB, and USB. Choose your favorite and make sure to adjust the address string as necessary. You'll find examples of use of the dir method so that you can learn about the Python driver, and then how to make all of the parameter adjustments that are outlined in the basic lock-in Getting Started guide. That is, how to adjust the sign out amplitude. These are organized into sections over here. How to query measured values, adjust the phase and frequency, understand input range and signal overload behavior, and adjust the sensitivity, time constant, and filter settings. Finally, as a bonus, I've added a demo measurement sweep where some initialization is grouped together into cells that you can execute, adjusting the values as necessary. And then the DC offset of the sign out is swept from -1 volt to 1 volt in 100 steps, and X, Y, R, and theta are recorded using the getChannelValues method at each offset step, following an appropriate wait time. This kind of sweep could be used to record a differential resistance measurement, for example. This notebook is available with the SR860 repository on GitHub, right here, Getting Started, and you can actually just view it directly in the browser. I hope this helps get you started writing Python code to automate your data collection with an SRS lock-in amplifier. Thanks for watching, and good luck with your measurements.